Preparing to live stream the meeting on YouTube. Done. Redirecting you to YouTube. A problem occurred with this page, so it was reloaded. That could just be my browser. All right. This is a laptop I don't often use. No. Copy streaming link. Right. Can I see myself looking very bored and very annoyed? Right. Okay, there's a good chance that I am now on that very same URL. Hang on. Oh, I can see. Oh, there are. I can see myself on the screen. Okay. Can you all see me? I think yes. Hello, you are live. Patrick, hi. Stand by 1 minute. Lee, I think we're there, Lizzie. Do you want to wait until for 15 minutes? Because we've told people to come back at 1:30, haven't we?
I mean, possibly. I can see you.
I know.
I reckon, Mark, you just keep going.
Shall I just keep going? Okay, bye-bye. Right. Good afternoon, everyone. Apologies for this hideous delay. I have got laptops and devices galore scattered around me. We've had lots of technical challenges with this broadcast. So welcome to today's Earth Live lesson, arranged, of course, by the wonderful Lizzie Daly. So this is going to be a little bit different. My name is Mark Thompson. I'm an astronomer, a broadcaster and author. It's going to be a little bit different to the previous live lessons that you have been tuning into, because as an astronomer, I don't look at the Earth. My role is to look out from the Earth into space. So you've done lots and seen lots around lots of different creatures and habitats around the world. But what I want to do is put it all in context a little bit and give you a feel for our place in the universe. So that's the purpose of this session, really, is to give you an understanding of where the Earth is in space. And I'm going to do that, attempt to do that using a desktop. Now, I've got using a telescope in Hawaii. Now, I just need to try and share my desktop. So let's see if this works. So while I'm doing this, I've done astronomy has been a passion of mine since I was about 10 years old. And it's taken me to lots of wonderful places, to the top of mountains at Palma, the Canary Islands, to wonderful observatories, but also down to the depths of the Earth. I went down some salt mines in Bolby, in North Yorkshire, where there's a dark matter detector. And of course, in the world of astronomy, to study the universe, we don't just look at light, we don't just look at the visible wavelengths of light that you and I look at as we use our eyes. We use the whole range of the electromagnetic spectrum, which ranges from radio waves, infrared waves, all the way across to ultraviolet, gamma rays, X-rays, microwaves, all those things you've heard of. But we also use other methods to study distant objects, and dark matter, studying dark matter is just one way we study the universe. And down the bottom of the salt mine, which was a kilometre underground, there was a dark matter detector. And it was wonderful to go underground to study the universe above our heads, which is really quite cool. So hopefully you can all see my screen now. I'm going to just try and refresh the view so I can try and see what you people are seeing. And what I want to do today is I want to try and give you a feel for where we are in the universe. And I'm going to start. So what you can see, hopefully you can see, is a screen which is the control screen of a telescope in Hawaii. Now in Hawaii, we are very fortunate that the skies, as you can see there from the current sky view, the skies are utterly amazing. And by placing telescopes on top of these mountains, we can see the universe a lot clearer. So the telescope I'm going to use this afternoon is a 0.4 meter telescope, which, you know, it's 40 centimeters in diameter. It's got a 3 meter focal length for anyone who is interested in the optics of the system. And what we're going to do is we're going to use this to take some images of objects around the universe. I'm going to start off with trying to kick off an object which is really quite wonderful to look at. It's called M17. I can just pick off the object's name. down this list. In fact, I can't pick it on there because it's not there. Instead, what we'll go is we'll go for M16, which is another object which does look rather wonderful. It's an object that's otherwise known as the Eagle Nebula. So I can specify which color filter. I'll explain that in a few moments. I'm going to go for an exposure of 240 seconds. In fact, first off, I'm going to go for 10-second exposure to make sure that the object is indeed lined up. So what's happening is that the telescope will now move across the sky to this thing called M16, which is the Eagle Nebula. And in a minute, we'll take a nice high quality image of the nebula. And the reason I wanted to take a picture of this and show you is because the Eagle Nebula is a vast cloud of gas and dust, which we can see in the night sky. And of course, that's where the Earth came from. So around 5 billion years ago, the Earth evolved, formed out of a gas cloud, very similar to this object that we're about to see an image of. So any second, my initial 10-second observation. So there we are. That's the image you can see there of the Eagle Nebula. And I'm going to try a longer exposure. I'm going to go for 240-second exposure. I'll kick that off, and then we'll see a much higher quality version of that image. And as I say, it's a gas cloud, so it's made up of hydrogen, be some other elements in there as well, bits of oxygen, carbon, some bits of dust as well. And what happens is these gas clouds are sat in space, floating around, and to start off with, we tend to find the electrostatic force is the first force which causes things to change. Now, I'm sure you remember from your days as children, and if you're a child now, of course, you may have done it recently, but if you can, while we're in lockdown, get a balloon, rub it on your hair, and you can either make your hair stand on end as your hair gets attracted to the balloon, or you may be able to make the balloon stick to the wall. And what's happening is the electrostatic force between the balloon, between the atoms in the balloon and the atoms in your hair or the wall cause an attraction. And because we get this attraction, it causes things to stick together. And in these gas clouds, just like M16, the particles of dust, gas, they start to stick together through the exact same force which causes a balloon to attract our hair or to stick to the wall. So the electrostatic force starts off by causing the gas and the dust particles to stick together. And as they get larger and larger, we get these clumps of material within the gas cloud, and eventually they get large enough that gravity can take hold. And when gravity takes hold, the clumps start to get really big. And those clumps, those sort of localized clumps of matter, are actually what cause, or actually the precursor to stars being formed. And as they get larger and larger, the pressures, the forces compressing on the core of the star cause the hydrogen in the core of the star to start crashing together. The hydrogen atoms start crashing together to produce helium atoms. And when that happens, that's effectively the birth of a star. And so our sun started life like this from a gas cloud, just like the gas cloud you saw in M16. I'll show you again on this picture down below. You can see here, we've got these dark, long tendrils. Now, I'll give you an idea of scale of this object. This arm, this was actually taken a wonderful picture by NASA, took this picture called the Pillars of Creation. Have a search for it. It looks amazing. And these gas tendrils, they're about a light year in length. Now, a light year is the distance that light can travel in 1 year, and that's about 9 trillion kilometers. Now, the distance to M16 is about 7,000 light years, and we use the term of a light year in astronomy to determine distance, or rather to articulate distance, simply because you imagine 7,000 light years, 1 light year is 9 trillion kilometers. That number is going to get very, very big, very, very soon. So in astronomy, we don't use kilometers, we use light years as a measure of distance. And so the length of that arm is 1 light year. So light would take 300, or traveling at 300,000 kilometers every second, light will travel that length in about a year. This whole thing is about 7,000 light years away. So the light that's hitting the detector on the camera, which is on top of Mount Haleakala in Hawaii, which is about 12,000 kilometers away, has been traveling for 7,000 years. So actually, when we're seeing this image, and indeed when we look at objects around the universe, we get to see them as they were thousands and thousands, if not millions of years ago. So actually it helps us to understand the evolution of the universe, because we are effectively looking back in time. And it's easier for perhaps for us as physicists to study the universe and to build up a story of how stars and galaxies evolve, because we can look at the stages of evolution in the sky nice and easily. So as you'll see, the image has just finished. So that image is now going to be downloaded. It takes a few seconds for the image to download. There we can see the camera is now reading out. In fact, if you can imagine these digital cameras that we use on telescopes, black and white, so it only takes a black and white picture. But what it does, it's like a grid of solar panels. So each individual solar panel, tiny little solar panels, just a few microns across, every time it detects a bit of light, the more light it picks up, the higher the voltage it creates. So the solar panels, the sensors inside the cameras, produce an electrical voltage which is determined by how much light it's receiving, and the more light, the higher the voltage. And we can do that, use that to create a real image of the amount of light. So this is the picture we've just taken, but if we have a look, this wonderful system which is run by the Las Cambras Observatory, which is a wonderful educational facility which schools can sign up to. It also does produce a processed version of the image as well. So I'm going to click on this and we should pop up an image which is then automatically processed to enhance the object we've just looked at. Here it comes. I'll just, there we go. So let's look at that. So you can see the wonderful level of detail. So this is the gas cloud out of which stars will be forming inside these more dense regions of the gas cloud. You can see it's called the Eagle Nebula. I kind of think it's this sort of bit that makes it look like an eagle. You can see its beak at the top. I know you wildlife people are probably laughing and scoffing at me for saying this looks like an eagle, but you can see the top of the beak, the bottom of the beak, and then you've got the wings out at the back here. So this is the Eagle Nebula, a structure in our galaxy just 7,000 light years away, which we've just taken a picture of from a telescope in Hawaii, that allows us to see how and where our Earth formed from about 5 billion years ago. So that's the Eagle Nebula. I'll leave that there and we can perhaps go back and look at that a bit later on. But what I want to do now is I want to take a picture of another object, which is called, in fact, before I do that, I'm going to take a picture of the same object with a green filter. So I'll kick that picture off and I'll explain why we do that now, in fact, because what we do, if you have your phones or your digital cameras, your digital SLRs, then what we can do is we use color sensors in those digital SLRs or in your phone. But what that means is that instead of having a grid of black and white sensors, or sensors that just measure the amount of light they're receiving, what we have to do is we have to have one of those sensors has to be covered by a red filter, one has to be covered by a green filter, and one has to be covered by a blue filter. And because we're covering all these different things by filters, that means that actually every 4 sensors, or pixels as we call them, are used to make up one piece of color information. But on a black and white camera, we just use one of those sensors to build a portion of the picture. And what that means in real terms is that a black and white camera will give you a much finer level of detail than a color camera. But of course, we want to see color pictures of the universe. So what we do instead is we use the black and white camera to give us the sense, or the resolution, the quality of detail that we're looking for. And in doing that, we have to find some way of constructing a color picture. And we construct a color picture by using filters. So what we'll do is we'll create an image through a red filter. As you've just seen with the image we can see here in the live webcam image is of a red filter. We can then use, we'll take another picture of the same object with the same black and white camera through a green filter, and then another one through a blue filter. And by the time we've combined all those filters to get all those images together, we can then see, we can actually recombine them in processing. I'm just going to upload or fire up my other laptop because I've got 3 machines here. None of them are showing me what you folk are saying. So I'm just going to try and fire this up while I'm talking to you. So we have to create these individual color pictures using a black and white camera which we then combine again in processing once we've taken all the pictures, and that will give us a color picture, which is what you really want to see. And all these wonderful images you see from the Hubble Space Telescope and the amateur astronomers create and look at of the night sky are all created using color filters on black and white cameras. So I think I've now actually got the ability to see what you people are saying. So let's just see how the image is doing. We've got 97 seconds left to go. And what we're going to do after this is I'm going to take a picture of another object, which is going to show truly, well, not truly, but it's going to show us where we are in the universe. So I'll see some pictures. I can actually see what people are saying now, which is wonderful. We'll come back to some of those questions towards the end. And one other thing we do, we don't just use red, green and blue filters when we take pictures of the night sky. We also use different types of filters. So we have hydrogen alpha filters, we have oxygen filters, and we have sulfur filters. And what they give us the ability to do is see a much finer amount of light, so we can actually get really high quality images, and we can actually start to learn an awful lot more about the material that's there by using different filters to give us a little bit more of an insight into what's visible. Now, this nebula that we're looking at has got an awful lot of hydrogen gas in it, and that's why hydrogen gives off a lot of red light. So you'll see once the the green picture comes down in just 26 seconds, you'll see that there's not as much light hitting the sensor in the green wavelengths as there is red, and that's because these gas clouds are mostly made up of hydrogen gas. And we can see lots of examples of gas clouds like this. For example, the Orion Nebula in constellation of Orion, not surprisingly, is another region where stars are forming, and that object can be seen with the naked eye, although it's not a good time of year. If you looked at the skies over the last couple of nights, or the last couple of months rather, you would have seen it very, very nicely. But it's too low now, and it sets just too soon after the sun has set. So I think the last green image has now just completed. So we should see that appear in here any second. I think this might actually be the green image now. So let's have a look at the two and we can compare them. So we've got the red image that we just looked at. Let's look at the processed green. Let's download it. This is the processed green image. So here we have the red image that we looked at earlier, and notice how much detail there is in red and how strong the signal is. But if we look at it in green, you'll notice that there's not as much detail at all. And that's because, as I've said, we use the different filters to pick out different levels of detail. We've got green there, which there's not a lot of green light coming out of the nebula, but there's a lot of red light. And of course, allowing us, using this technique, we can build up color pictures, true color pictures of the universe. Okay, right, so what I want to do now is move to a different object. And this time I was going to look at a galaxy called M101, which interestingly might have got just a little bit too low now. So instead, I'm going to go for NGC 6643. Nice name to reel off the tongues. Let me just kick off a quick image of that just to make sure that when it gets there, that it is centered in the field of view of the telescope. So that's now, the telescope is now moving across. I'm trying to multitask with lots of different machines all at once. It feels like I'm actually operating a real telescope at the moment, which is really quite wonderful because, like I say, it's a telescope that's completely unmanned, but it does mean that I am able to use it and control it completely from here in the UK. So what we're looking for, we're looking now at getting a picture of a galaxy which is in the constellation of Draco, not anything to do with Harry Potter, I'll hasten to add, in the constellation of Draco, but it's so far away from us that it's at a distance of 65, I think it's 65 million light years away. So we were looking at the Eagle Nebula at a distance of 7,000 light years. This thing is 65 million light years away. So we can see just about got the fuzzy nucleus of the galaxy. So what I'm going to do is I'm going to go for I think I might go for a 240-second exposure of this object as well, because it's going to be easier. Basically, the longer you expose a camera on the sky, then the greater the level of detail that you will see. Now, this is a galaxy, so it's 65 million light years away. And what I particularly want to show you this for is because we live in a galaxy called the Milky Way, and the Earth lives in a galaxy called the Milky Way. And that galaxy is just one of a vast, vast universe. Now, our galaxy, the Milky Way, which you can see at this time of year nicely sort of looping up above the horizon, typically up from the east and looping around the northern hemisphere, so the northern part of the sky to the west, over to the west. And when you look at it, you don't realize, but you're looking at the combined light from millions and millions of stars. In fact, we now think there are between 300 and 400 billion stars in the Milky Way galaxy, and our sun is just one of those stars. There's nothing particularly special about our sun. It's not particularly hot, not particularly cold, it's not particularly big, and it's not particularly small. In fact, there are larger stars that if you put them where the sun were, they would swallow up almost the entire solar system. So our sun is pretty average, and we're one of 8 planets orbiting around the sun, which, as I've said, is one of about upwards of, or just up to 400 billion stars in our galaxy. Now, if we look deeper into the universe and we see lots of galaxies across the universe, we can see that actually there are millions upon millions. In fact, latest count is that there's probably about 100 billion galaxies, at least 100 billion galaxies in the universe. And the way we can sort of work that out, the way we compute how many galaxies there are in the universe, is to take a look at the portion, look at a tiny portion of the sky, and looking at a tiny portion of the sky, we can count how many galaxies are in that tiny portion of the sky. And if we then multiply that by the rest of the sky, we can get an approximation of how many galaxies there are in at least the observable universe. And that's the universe that we can see in the night sky. So we use that sort of technique of estimating to gauge how many galaxies there are in the universe. And actually, if you think about it, we are fairly insignificant. So we're on a planet, one of 8 planets orbiting around a star, pretty average star, in a galaxy where there's between 300 and 400 billion stars, and there are upwards of 100 billion galaxies across the universe. But what I think is really interesting, I'm sure it will resonate with you folk, is that the only place that we know of for absolute certainty where life has evolved is here on Earth, which is really quite remarkable that life has evolved here on Earth. So this galaxy I want to show you really just to give you an idea of where we are in our galaxy. So our galaxy is a spiral galaxy. This is also a spiral galaxy. I mean, hopefully you'll see the spiral structure in the image in a few moments. But galaxies do come in a number of different shapes, certainly, and sizes. Our galaxy is spiral. So if you imagine 2 fried eggs, the good analogy is 2 fried eggs stuck back to back, then the yolk of the egg gives you the sort of bulge at the top and the bottom. And that yolk bulge is the nucleus of our galaxy, where the great proportion of stars are. But then sort of streaming out around the yolk, almost along the plane of the white of the egg, is where you'd find the spiral arms. And that's the spiral galaxy. And like I said, you'll see an image of a spiral galaxy, hopefully, shortly. But there are other types of galaxies. There are barred spiral galaxies, which are like spiral galaxies, but they have got a bar across the center. And then there's also elliptical galaxies as well. And we think that ours is a spiral galaxy. So this image is now reading out from the camera, and we'll just take a look. There's the sort of the raw image, but let's have a look and see if we can see a preview image of what that, oh, that's the wrong one, processed image. That's the raw one. I clicked on the wrong button. Has it actually processed it yet? Oops. Takes a little while for this processing. Interesting, when you take astronomical pictures, the vast amount of time is spent processing the images. Once you've taken the pictures is the easy bit. Once you've got them, that's when it gets hard, and that's when you have to start loading up all manner of different bits of software to try and process them. But this is the raw, the processed image, and there's a little bit of tracking issue there, but still we can still see. Let's just zoom in a little bit. This is the nucleus. Remember I said about the fried eggs, and this is the yolk, the yellow bit of the egg. We've definitely got some tracking. This is a major problem for astronomers, that the Earth spins. Who'd have thought it? And because the Earth spins, that means that everything moves across the sky. You're all familiar with the sun, moon, and stars rising in the east and setting in the west. That means that with astronomical telescopes, this telescope has taken a picture which took about 4 minutes to capture a telescope, given that we're magnifying the object we're looking at. What we're also doing is we're magnifying the rotation of the Earth. So we have to have cameras and telescopes that point in the opposite direction, point in the direction of the thing you're looking at, but they spin in the opposite direction to the Earth, but at the same speed. So they kind of counteract the rotation of the Earth. And as you can see, the tracking or the guiding of this telescope is slightly off because we've got these little lines instead of pinpricks of stars. But you remember on this previous picture of the, what's happening? Oh, come back pictures. The previous picture of the nebula, of course, we've got nice pinpoint stars. But going back to our galaxy, this is our galaxy NGC 6643. There's the nucleus, and you can just about make out the spiral arms which are emanating from the galaxy. And if this was our galaxy, if this was the Milky Way galaxy, then we would be around about there. We're about sort of 2/3 of the way out. So we're kind of there in a spiral arm in our galaxy. Now our galaxy is where we're inside, so we'll never get a picture from the outside looking in to our spiral galaxy, but still we can look at other spiral galaxies, and we're pretty sure ours looks probably something not too dissimilar to this, with, I say, these spiral arms, and as I say, we're about 2/3 of the way out from the center. Now I have actually got a couple more minutes I want to say, so we can have a look at maybe taking another picture. Let's just see what else is in the sky. We might find actually we're going to run short on time. Let's just see if there's any other objects we could. I'll tell you what, let's have a quick look just to talk about the end of the solar system. So there's going to be a point in time, I'm afraid to say, that at some point our sun will die. I'd like to hear a collective "ah" from you all, from wherever you are. At some point our sun will die. So let's just move across to this object just as a last little picture before I sign off. I'll explain what it is in a few moments. Let's just let the telescope slew across, because all stars die, sadly. Our sun will die probably in about 5 billion years, just under 5 billion years time. And when it does, that will mean the end of life on Earth, certainly at this location, because there is a chance that we might move somewhere else to around another star system by then. So what I'm going to do is take a quick picture of this object as a final little object. So the preview image will come down, and this will give you a feel for how life on Earth will definitely end one day. There will be phases of extinction. I know Ben Garrett is working on a book about the various different extinction events through history. But there it is. There's a raw image. I'm just going to do a quick 2-minute exposure. I think that's all we need for this one. And there are going to be occasions throughout the history of planet Earth where life will end of various different degrees. We had the extinction of the dinosaurs, and in fact, I can share with you it was something like this, although probably a little bit bigger, I would think. So this is an example of a meteorite. This is a shooting star, which you may have seen whizzing across the sky at some point throughout your life. Excuse me. And shooting stars, nothing to do with stars at all. They are pieces of rock. And this is a meteorite, an iron meteorite. So inside this is a solid chunk of iron, might have a bit of nickel mixed in with it as well. But these things fall through the sky. And as they come through the atmosphere, they warm up, they kind of cause the gas in the atmosphere to glow as they plummet towards the Earth. And then when they finally land, we call them meteorites, and if we're lucky, we collect them. We often actually mount exhibitions to the Arctic or the Antarctic to go and find these things, because these are much easier to find if you go to polar regions, because they stick out like a sore thumb. Try and find one of these in your garden, it's going to be really tricky. So this is a meteorite, and it would be something like this, much larger, that caused the extinction of the dinosaurs. But ultimately, life on Earth will come to an end somehow when the sun dies, which will be in about 5 billion years. And for the most part, the sun is stable because the force of gravity is causing the sun to try and collapse. But at the same time, the thermonuclear force, which is created from fusion of hydrogen in the core of the sun, is starting to try and expand the sun. And for the most part, that's stable, but eventually the thermonuclear force wins. Force of gravity is not able to hold on to it, and the star blows itself. Doesn't blow itself to pieces violently, but the outer layers certainly will get blown out into space. Let's have a look at a couple of the questions. Oh, thank you, Mark Anthony, for your R. I could almost hear you from here. Question from Emily: how long have I been interested in the night sky? Good question. I would be giving away my age if I told you. I got interested in astronomy when I was about 10 years old, only about 20 or so years ago, and I saw Saturn through a telescope of the Norwich Astronomical Society, where I'm the president. And when I saw Saturn through a telescope live, it got me absolutely hooked, line and sinker, for astronomy, but also for science in general. And one of the things I like to try and do, you know, as does Lizzie with all her marvelous work, is try and get kids excited about science. And that's why that's what kind of got me into it. So it was when I was about 10 years old. In reality, about just over 30 years ago now, giving away my age. Any other questions on here that are of interest? Few people having problems. Oh, that's okay. No, that's an earlier one. So Mark Anthony asking, did NASA color in their pillars of creation photo, and is it artistic impression? No, absolutely not. They used the hydrogen alpha, the oxygen, and the sulfur filters. So they certainly may have been enhanced, but they were not colored in. They were how the object would have looked looking at it with those filters. So it's a true color image through a very specific set of filters. And that's usually the case with astronomical pictures. So let's just take a last look at this object, which should appear now. It's not low. There we go. There's the live image. So there's the live picture. And let's have a look at the process. So man, this is an object which has a star which has died, and this will be the ultimate fate of the sun in about 5 billion years, and ultimately the Earth. There we go. This is all the outer layer of the star that went pop at some point in the past, and just in the center there is the core of the star, which is left behind. But that's it for me. I think it's time for me to tune off. I'm sure Lizzie has probably got to go and have probably a strong gin and tonic now, Lizzie, given that the stress levels we had getting this started. But thank you all for tuning in. I hope you enjoyed it. If you have enjoyed yourselves, then do follow me on Twitter if you don't already. I'm People's Astro, and I've been having lots of fun over the last few months guiding people around the night sky via Twitter. So follow me on Twitter. Also, of course, a plug for my latest book, which has got 101 facts you didn't know about space. And my favorite fact, one for you wildlife lovers, is that dung beetles use the Milky Way to navigate. I shall leave you with that. If you want to know more, then you can get my latest book in all good bookshops. But it remains for me to thank Lizzie for her patience in getting me up and running today. We got there eventually. Thank you, Lizzie. Thank you all for joining in. And don't forget, there are still more Earth Live lessons coming up over the next few days. Do please tune in. Thank you all very much, and I hope you've had fun. Have a lovely afternoon.